Hi, we are going to move forward into more Chapter 6 material, specifically statistical power, sometimes just called power. And power is the ability to correctly reject the null hypothesis. So if you recall from a previous lecture, this grid, it's a 2x2 grid that shows us the possible outcomes of our research study. In our research study, we may either reject or fail to reject the null hypothesis. Those are the only two outcomes of our study. And in the real world, there are only two possibilities: that the null hypothesis is true, or that the null hypothesis is false, or in other words, the research hypothesis is true. So that combination of possibilities results in 4 different potential outcomes. Remember that we could be making a type 1 or type 2 error in our study if we draw an incorrect conclusion. So we could reject the null hypothesis when in fact in the real world, the null hypothesis is true. So we shouldn't have rejected it. And that would be called a type 1 error. We could also fail to reject the null hypothesis, or in other words, we miss some sort of statistically significant effect that in the real world exists. And that would be called a type 2 error. The other options are that we don't reject the null correctly because the null is actually true. Or in other words, we say in our study, there's nothing going on here, and we're right about that. Or sometimes we may find that there is a statistical effect, that there's a significant effect, that the groups are significantly different, or our intervention actually has some sort of effect, and we're correct about that. So in other words, the research hypothesis is true, the null hypothesis is false, and we conclude to reject the null appropriately. In our studies, that last option, correctly rejecting the null hypothesis, is called statistical power. And often that is our goal. It's the goal of our research studies. What we often hope to find is some sort of effect. And of course, we hope to find it correctly. We hope that we're finding it and that it's not just by mistake. Okay, so that's the goal. We're really shooting for the upper right-hand corner of this grid. The research hypothesis is true, and in our study, we support that. So assuming that the research claim is in fact true in the real world, I just want to call attention to this red square or outline that you have in the grid. If the research hypothesis is true, then there are only 2 options in our study. We either reject the null hypothesis or we fail to reject the null hypothesis. So we can either fail to reject the null, making a type 2 error. Or alternatively, if we don't fail to reject the null, we reject the null appropriately, and that is our statistical power. Because there are only 2 options, those probabilities must add up to 100% or to 1. So in other words, if the research hypothesis is true, then the probability of making a type 2 error is beta. You know that from a previous lecture. So the probability in that case of power, or of correctly rejecting the null, is equal to 1 minus beta. And that must be true because beta and power must equal 100% or 1. So just to summarize, the definition of statistical power is the probability of detecting an effect when in fact the effect exists in the real world. And that probability is equal to 1 minus beta. I'm just going to lay out an example here, and I'm going to pull in some of the information you learned in a previous lecture. So let's imagine that there's a new treatment for memory for older adults. And we have a study population or a study group who gets a special treatment to improve memory. And that group actually does perform better than an untreated population on memory tests. And the magnitude of the difference, recall, would be effect size. So the difference between population 1, the treated population, and population 2, the untreated population, is effect size. In this case, the memory test scores have a population mean, so this is the comparison population, the untreated group, of 100 with a standard deviation of 15. And in the treated population, the average memory score is 106. And remember, because of our assumption of homogeneity of variance, we will also assume the standard deviation for this population is 15. So note that the two means on the memory test differ by 6 points. And those 6 points correspond to 4 standard deviations. So the effect size here is 0.4, which means that the two population means are exactly 0.4 standard deviations apart. And remember that that's about a medium effect size. And you can visualize that here in this diagram. We have our comparison population, or the untreated group, in blue. They have a mean memory score of 100. And the treated group in red, this is the population of individuals who get the memory treatment, and they have an average score of 106. And you can see that the comparison population has scores that range from about 90 to 110, and the treated population has scores that range from about 95 to 115. And importantly, the distributions do overlap a little bit. So let's just break this down a little bit further. You can see that there are individuals who belong in the blue distribution purely. So these values, these are actually, I should more appropriately not say individuals, but possible sample means that specifically fall in the blue distribution. These are sample means from the population of people who are not treated. So they are from that population, and in any of our studies, we would accurately detect that they belong in that population. And then there are also sample means that specifically come from the red distribution, or the treated population. And in any of our statistical studies, we would accurately be able to detect them as members of, or as samples from, that population. However, because the distributions overlap, there are values, we're going to get some sample means that cannot be easily distinguished between population 1 and population 2, because they're values that could belong to either distribution. So these values are part of the red distribution. Let's say they're part of population 1, the treated group. But we might believe that they belong to the blue group because we were not able to detect a significant result, right? So those values belong on, you can see that those values exist to the left of the critical value on the comparison distribution. And let me just show you where that is. There's this critical value right here in the comparison distribution. You can see 5, because the alpha level is 0.05. In this shaded area, 5% of scores fall in that shaded area on the blue distribution. So there are some people in the red distribution that we will mistake for the blue distribution because they aren't different enough from the blue distribution mean that they fall past our critical value. And I know this is a little bit complex, so I do encourage you to read the textbook chapter on this, watch this video maybe a couple times, and let me know if you have any questions. So just going back to what I was saying, there are going to be people where this arrow is pointing here. This group of people, or those samples of people, will lead to values that are not extreme enough that they fall beyond a critical threshold on the blue comparison distribution. So we will say there's no difference. This sample is no different from all the other blue samples, right? There's no effect here. But notice that that is equal to beta. That would be a missed effect because they are in the red distribution. Those are people who are significantly different than the people in the blue population. So those values are part of the lower end of the red distribution, but we mistake them as being on the higher end of the blue distribution, or in other words, we mistakenly assume that there's no effect, making a type 2 error. And in this little diagram, there's a 36% chance that we're making a type 2 error. And then importantly, there's also going to be sample values that fall out in this region here that are part of the blue distribution, but they're really rare on the blue distribution. And in fact, they're so rare and unusual for the blue distribution that we think they're most likely going to be part of the red distribution. Or in other words, we say this value that I got in my study that I observed is so far away from the blue distribution mean, right? Because that's over here. That's far away from the blue distribution mean. So I think it must be part of the red distribution. I think this sample is part of its own distribution. It's unlike the comparison distribution, or in other words, there is a distinction here. However, don't you see that those are actually part of the blue distribution? They're in the tail of the blue distribution. It's just unusual. They're just unusual values for the blue distribution, but not impossible. So I could mistakenly reject the null hypothesis if I observe one of these values here, and I would be making a type 1 error. Okay. Now let's talk about how you compute statistical power. So let's imagine that we're running a study on impulsivity, and the mean of our sample is 208 on an impulsivity scale. So that's M equals 208. The comparison population has a mean of 200. So population 2 has a mean of 200, mu equals 200, with a standard deviation sigma of 6. If we wanted to calculate statistical power that we have in this study to detect a significant difference in impulsivity of a one-tailed test. So what we're going to do is draw a second distribution in addition to the one that we've been drawing. So we usually draw the comparison distribution, which has a mean equal to our comparison population. Now we want to also draw a distribution with a mean equal to population 1, our population of interest. So in this case, it's 208. And I mark the raw value associated with the critical value on the other distribution. So in this case, I'm drawing a distribution with a mean equal to 200. That's the one we always draw. I know that my critical value on that distribution, if I'm doing a one-tailed test with a significance level of 0.05, is equal to a z-score of 1.64. And that's always, remember, the critical cutoff value for a one-tailed test at the 0.05 significance level. So the critical value is 1.64. I can convert that backwards using this formula into a raw value from a z-score. So I can figure out what impulsivity score corresponds to this threshold. Right? So what impulsivity value would my sample mean have to surpass for me to have rejected the null, or for me to have drawn a test statistic that would fall in this region. So this formula here will allow me to transform my critical value from the z-scale back to its raw scale version. So in this case, the critical value of 1.64 on my null distribution corresponds to a raw value of 209.84. In other words, if my sample had a mean of at least 209.84, then I would have rejected my null hypothesis for this study. Now I want to draw a second distribution. And remember, this distribution should have a mean of population 1, which is our sample mean. I draw the raw value that I just computed on this distribution. So I map it onto this other distribution. Okay, so you can see 209.84. Now this is the new distribution that I've just drawn. This is the second distribution. It has a mean of 208. That's my population 1 mean. This is the one I've always been drawing down here. Okay, so the one on top is the new distribution that we're drawing for the sake of computing statistical power. It has a mean equal to population 1, and I wanted to put this raw value that corresponds to the critical value on the null distribution. And then I want to figure out what z value that corresponds to on my new distribution. So 209.84 on the bottom distribution corresponds to a z-score of 1.64. But 209.84 on the top distribution corresponds to a z-score of what? So I'm using my z formula here. Z equals x minus m over the standard deviation of this distribution. So x is the value that I want to find a z-score for. So 209.84 minus the mean of the distribution, 208, over the standard deviation of the distribution, which is 6. And that gives me a z-score of 0.31. So on the top distribution, a value of 209.84 corresponds to a z-score of 0.31. Now I can look in the z-table for z of 0.31 and figure out that the percent in the tail is equal to 37.83%. Or in other words, about sampling from population 1, 37% of the values from population 1 would surpass the critical value that we use for our statistical test, right? Because that's this value here. So that means that power is equal to 37%. And if that's not clicking, it's because 37% is the proportion of individuals who actually belong in population 1, right? That's that population I've just drawn a box around, and simultaneously who we would conclude belong in population 1 because they've surpassed our critical value. So we reject the null hypothesis for all values in this area, and we would be correct about it. So just some notes here. Imagine that our sample mean was 216. So the comparison population mean stays the same, but our sample mean now is 216. So there's a larger effect size. If we imagine that there's a larger effect size here, then there's less overlap of the distributions, resulting in increased power. So in other words, the important piece of information down here, as the difference between the means increases or effect size increases, then power also increases. Also, significance levels affect power. As alpha level, or the significance level, decreases, power will also decrease. And you can envision that. Other things that influence power could be variance, right? Decreased variances, increased effect size, and therefore increased power. So if there's more spread in the distributions, then power is decreased. If there's less spread in the distributions, power is increased. Also, sample size. As sample size increases, then we have lower variation in our distributions and we increase our power. This one is really important because we have control over it. Okay, so we have control over this one here. We can decide to collect more information or to collect data from more individuals if we want to increase our power. But it's also to be taken with caution because sometimes you'll see that studies find significant findings with really tiny effect sizes. And that's usually because the study is overpowered with a huge sample size. So you can get a huge sample and statistically detect a difference that's really, really tiny. So that's one to be aware of and also to be cautious of sometimes. And that's the end of my lecture on statistical power. Again, I know that power is really complicated. This actually tends to be one of the toughest concepts for students to grasp. So if you don't understand it, don't worry about it. Just let me know if you have any questions and you can discuss it in the discussion forum.